All right, section 3.5, we're going to talk about derivatives of inverse trig functions. So today the goal is, let's review trig functions one more time, and then let's talk about the inverse trig functions, and then eventually leading to finding the derivatives of inverse trig functions. Okay, a little background information. Remember that an inverse function can only occur when you have a one-to-one function. That means that the function has to pass the horizontal line test in order to have an inverse. If it does not, you have to restrict the function, basically like shrink it, so that it is one-to-one. So here on this slide, you'll see the sine wave obviously is not one-to-one because it does not pass the horizontal line test. So in order to make it one-to-one and make it have an inverse, you would want to cut it down so that there's only a piece of the wave that is now one-to-one. So that's what the right graph looks like. That's the sine wave cut down so that it is one-to-one, and an inverse is created from this. So let me show you real quick on Desmos. Here's my sine wave. And again, I'm just going to cut it down so we just see this little section here in the middle. So that would give me with this little piece here. The inverse sine function would look like this purple line. Remember that inverse functions are reflected across the line y equals x, and you'll see that your sine wave and the purple inverse sine function are exactly that. They're mapped across this line. So what I am trying to get at here is that because we've restricted the sine function down, that affects the range of your inverse function. Okay, so it is very restricted. There's only certain values you can plug in to an inverse function as far as trig inverse functions go, and there's only certain answers you can get from them as well. Okay. This slide, we're going to do a little practice so I can show you how to find values on inverse trig functions. So the first question down here says, evaluate the inverse sine of 1/2. So when you do this, you're going to ask yourself, sine of what angle is 1/2, or when is sine equal to 1/2? So this is a unit circle question. When is sine 1/2? And sine is 1/2 in a bunch of different places. Pi by 6 is one of them, 5 pi by 6, and I could keep going and list all of them. However, there's only one answer, and there's only one answer because the inverse sine function has to fall between, or the inverse sine answer, I guess, has to fall between negative pi by 2 and pi by 2. That's the range of possible outcomes. So 5 pi by 6 is bigger than pi by 2, so it will not be an answer here. The only answer that fits in this range of values is pi by 6. Okay, let's try another one. This one's a two-step question, and we're going to start here on the inside. Remember, arc sine, arc cosine, arc tangent, that just means inverse sine, inverse cosine, inverse tangent. So this means inverse. So this part we're going to ask ourselves, when is sine equal to 1? And so you're thinking with the unit circle, when is sine equal to 1? That would be at pi by 2, okay? So this inside value is going to be equal to pi by 2. And then you're taking tangent of pi by 2. And tangent, remember, is the slope. So what is tangent of pi by 2? Well, the slope at pi by 2 is undefined. So this answer is undefined. Okay, here's a quick graph so you have it in your notes of the sine function, but restricted down to create an inverse, and the inverse sine function, also called arc sine. This is what it would look like. And this is simply just to show you the domain and the range of each of these so that you know possible values that you can plug in and possible values you can get out of each one. Cosine, same idea. We have a cosine wave that's not one-to-one. So it also has to be restricted the same way that sine is in order to find an inverse. So when you restrict the sine wave, we're going to restrict it so that we're only looking at like half of one wave, and it would be, we're choosing to look at the positive side just so that we have positive numbers to deal with. So the sine or cosine wave is just going to be from 0 to pi, and that's going to create this guy over here that is arc cosine or inverse cosine. So this is my inverse cosine graph on the right, and this is my regular cosine graph on the left that's been restricted. Okay, so we're going to need to kind of look at those values as we compute things in each function. So first question, find arc cosine of radical 2 over 2. So you're going to say when or at what angle is cosine radical 2 over 2? That should be pi by 4. And you're going to do a quick check to see, is pi by 4 in the range of outputs for inverse cosine? It is. It would be down here. Is pi by 4 in the domain of regular cosine, the restricted one? It is. So that would be your answer. Something like 5 or 3 pi by 4 or 5 pi by 4 would not be acceptable because they are beyond the domain or the range values. Okay. Second question, we're going to go to the inside first, and we're going to say, what is the inverse cosine of 1? In your head, you need to be thinking, when is cosine equal to 1? What angle is cosine equal to 1? Well, cosine is equal to 1 at 0 degrees and at 2 pi. But we're going to use 0 because we're talking about inverses, so it needs to fit within this model. So this is 0. And then we're going to take cosine of 0, and cosine of 0 is equal to 1. Okay? Now, what you could have done here is you could have recognized that cosine and inverse cosine undo one another. And because this value is in the domain of inverse cosine, then you could just say that these two will cancel each other out, leaving you with 1. Same thing goes for tangent. Now, tangent's a little bit different because tangent is not a wave. Tangent has a lot of asymptotes, so it kind of goes up like this, like it looks like the cubic function actually, and it goes up like that over here, and it just kind of continues in that pattern. So for the tangent function, it kind of restricts itself naturally at negative pi by 2 and pi by 2 because there's asymptotes there. If you invert tangent to get arctan, you're going to have a wave also with asymptotes. The difference between this one and sine and cosine is this one continues on forever when you go to infinity or negative infinity. All right. Oh, this is supposed to say inverse tangent. Sorry, fix that. So what is the inverse tangent of radical 3? So this is, you're going to be thinking in your head, when is tangent equal to radical 3? When is tangent equal to radical 3? That should be, let's see, I believe pi by 3. And you're going to do a quick check to see, does pi by 3 fit in the range of acceptable values? It does. Okay, next one, when is tangent 1? So when is tangent equal to 1? What angle? Tangent is equal to 1 at pi by 4. Okay, and then this question, you're taking cos of pi by 4 as your next step. And I believe that is radical 2 over 2. Okay, one more little thing about these inverse graphs, and then we're going to move on to the derivatives of these functions. So with tangent, like I said, it does continue on forever, which means it's a little different than inverse sine or inverse cosine. So we can look at the limit of this function a little bit closer. So right here is just telling you that there's an asymptote, obviously, on the inverse tangent graph. And if it's just this limit statement here is just telling you where those asymptotes occur. So if you take the limit as x goes to infinity On the inverse tangent graph, you're going to get pi by 2. That's where it levels out. And then down here, you're going to get negative pi by 2 if you're going to negative infinity. So let's look at how we would do a limit problem with arctangent. So this one says, let's find the limit as x approaches 2 from the right of arctan of 1 over x minus 2. This is a complicated limit. So what we're going to do is we're going to use limit rules that allow us to look at one thing at a time. Okay, so essentially, let's move this limit statement inside and apply it to all this stuff in parentheses. Let's do that first. So then we're going to say, okay, how do I take the limit as x approaches 2 from the right? Well, to help you reason through it, what you could do is pick a number that is really close to 2, but a little bit bigger, and kind of plug it in for x. I don't know, 2.001 is pretty close to 2, but a tiny bit bigger. And if you do the math, you're going to get something like 1 over 0.001, which is going to give you, what, 1,000? Which is not important that it's 1,000. It's important that you look at the fact that this is going to be a big number. Because essentially what you're going to do is you're going to have 1 divided by some really, really small number. And when you divide by a really small number, you actually get a really big number, aka infinity. Okay? So what I'm looking at now is I'm looking at the second step. And the second step is see how arctangent gets affected when infinity is plugged in for its x value. So essentially you're saying, what is arctangent of x? Let me rewrite it. What is the limit as x goes to infinity? Because this is infinity of arctan. So that's the second part of the question. And that would be you thinking about the arctangent graph. And I'll go up here and look at him one more time. Come on. There we go. The arctangent graph as x goes to infinity means the right side. And we can see that there's an asymptote at pi by 2. So that means this must equal pi by 2. Now we're going to do one more thing, and this is super important. We have our answer, but we don't have it written in a way that says that we answered the question, because this says the limit as x approaches infinity of arctan is pi by 2. That wasn't the original question. The original question was, what's the limit as x approaches 2 from the right side of arctan of 1 over x minus 2? All that work we did gave us the answer of pi by 2. We just need to make sure we restate the question and its answer together in one limit statement. Okay, enough about limits and inverse trig functions. Now what we're going to move on to is derivatives of these inverse trig functions. So I'm going to do a little mini proof here with you to show you how one of the function derivatives come to be. And I won't do the proofs for any of the other ones just because you don't need to know how to do this. It's just a quick discovery thing for you, okay? So we're going to pose a statement. We're going to say if y is equal to the inverse tangent, then tangent of y is equal to x. And that's true because it's just the rule of inverses where the x's and y's flip, okay? So what we're going to do is we're going to take the derivative of tan y equals x. And the end goal is to find an equation for the derivative of the inverse. Okay, that's what we're going to be proving right now. So in order to do it, we're going to start here. And we're going to say, what's the derivative of tangent of y? Well, that would be secant squared y times dy dx, because the variables don't agree. Remember, that's the implicit differentiation rule. These variables have to match. And if they don't, you need dy dx to show derivative of baby. Derivative of x is 1. And we're going to solve this for dy dx. So we would get dy dx is equal to 1 over secant squared of y. All right. Now I'm going to go over and I'm going to show you a trig identity, sine squared plus cosine squared is equal to 1. This is a trig identity that should look familiar to you at this point. If you were in block last year, we did use these quite a bit. If you were not, it's nothing real crazy complicated. It's just a trig identity, meaning it's always true. Now this doesn't really apply to what we have in this problem because what we have is secant, not sine or cosine. So what I can do is I can divide every term by cosine, and I could create a new, still equivalent, trig identity that has a secant squared in it. Because 1 over cosine is the same as secant. So now I have a trig identity with secant in it. Okay, here's what I'm going to do. I'm going to use my trig identity, and I'm going to use substitution. So in place of secant squared, I'm going to plug in tangent squared of y. I want to remind you right now, this is not something you have to memorize. It's just showing you where formulas come from. Okay. And then we're going to go back and we're going to look at this one more time. I'm actually going to flip this around real quick. And I'm going to write it as tangent of y squared. But we're going to go back now to the original setup. And we're going to see that tangent of y is equal to x. So we can make that substitution here. And instead of tangent of y, we're going to change that to x. And now you have a derivative for inverse tangent that is all in terms of x. It is 1 over 1 plus x squared. Okay, so you just did a little mini proof there. Again, I'm not going to make you do that ever again. It's just to show you where things come from. So here's what I will do. I'm going to give you a little chart of all the derivatives of inverse trig functions with this little note at the bottom. AP has only ever tested inverse sine and inverse tangent. I have no idea why they picked those two, but those are the two you're going to see for sure on your AP test, none of the others. However, your textbook and Delta Math are probably going to ask you for all of these inverse trig functions at some point in time, so you do need to know them all. But I'm going to walk through a few examples of how to use these formulas, but they're pretty short and sweet. There are stars, though, besides inverse sine and inverse tan, because those are the two that AP tests. So that's what I'll focus on right here. All right, so how do we use those formulas? Well, what you're going to do is you're going to take the derivative using the formulas and sort of like a mama baby approach. Okay, so that's first, what is the derivative of inverse sine? It is 1 over the square root of 1 minus x squared, except x is not always going to be x. X might be your baby. Okay, so x might be your baby. So that's going to be the case here because we do have a baby inside. So it's going to be 1 over the square root of 1 minus the baby squared. Okay, that's step 1. Step 2 is you're going to also multiply by the derivative of your baby, which would be 2x. Okay, now sometimes the work down here at the bottom is easy to do algebraically and can help simplify your answer. So in those cases, you will simplify. You'll keep going with your algebra. I'm going to do that here just to show you what I mean. So I have 1 minus, I need to square this binomial next. So that's going to give me x to the 4th minus 2x squared, but that would become plus because of the negative on the outside, plus 1, but that would become minus 1 because of the negative on the outside. Okay, simplify even more, and you get the 1's to cancel, so you end up with the square root of 2x squared minus x to the fourth. I just flipped them around because I like the way that looked a little better. You can actually keep going. And again, this doesn't always happen. I'm just showing you what could happen. Down here at the bottom, you can factor out an x squared from each term. Like so. And then one more thing that you can do is these x squared. The square root of x squared is just x. So you could take that out of your radical. And then you would be able to cancel it with the x on the top. So your final answer is 2 over the square root of 2 minus x squared. That's your derivative of f. All right, let's look at one more derivative example. Find the derivative of inverse tan of cos. Okay, so we're going to do another mama-baby problem here. So derivative of mama is derivative of inverse tan, and that was 1 over 1 plus x squared. But we don't have x, we have cos x. So it's 1 over 1 plus cos x squared times the derivative of baby, which is negative sine x. And this time, I can't do a whole lot to make it look better, except call it 1 plus cosine squared x and put the negative sine x on top, and you are pretty much done at that point. Okay, that's it. You have a Delta Math assignment to go along with this lesson. Remember that Delta Math does have videos embedded in it, so if you get stuck, maybe look at those videos. If not, let me know and I can help you.